Okay, I want to do one more problem here where we're going to find the surface area of this part of a paraboloid, z equals x squared plus y squared, below z equals 5. Okay. And I want to do this two ways. Okay. Because notice, that's the same as saying z equals r squared. So there are sort of two very nice parameterizations that I could use, because here z is already a function of x and y. So I could use r of uv equals uv u squared plus v squared, simply letting x be my first parameter u and y be my second parameter v. Or I could use r of r theta, and I could say, well, x is r cosine theta, y is r sine theta, and z then is r squared. So this lends itself very, very nicely to just parameterizing, essentially using my rectangular coordinates x and y. I just like to have different names for the parameters so that I can say this is where I am in 2 space, and then in 3 space I get x, y, and z. Or r and theta, and essentially describing the surface in terms of cylindrical coordinates and using as my parameters just r and theta, and describing z then as a function of those. So I want to do this both ways because this will sort of allow us to explore the difference between setting things up one way and then switching to polar coordinates and setting things up using r and theta as my parameters from the beginning. Okay? We should get the same answer either way. Let's do this one first. So if I'm doing this one first, I know that I'm integrating over a region that would correspond to just the projection of this onto the xy plane. Now, if this is where z is equal to 5, that's essentially going to be a disk of radius root 5. So, my region in the UV plane is essentially just copying this disk. Right now, this is in the xy plane in 3 space. I'm just going to copy that into the UV plane. That's the region over which we're integrating, and I'll call that region D. Okay. So if I have this, the partial of r with respect to u, and by the way, if I did want to call that just r sub u, that's perfectly acceptable. I can use subscript notation for these partials as well. That would be 1, 0, 2u. And the partial of r with respect to v, which I could write if I wanted to as r sub v, that's just going to be 0, 1, 2v. Okay. So if I calculate the cross product, partial of r with respect to u, crossed with the partial of r with respect to v, that's going to be the symbolic determinant I, j, k, 1, 0, 2u, 0, 1, 2v. So that's going to give me, for the i's, I'm going to get nothing minus 2u. For the j's, I'm going to get nothing minus 2v. And for the k's, I'm going to get 1 minus 0. Okay, excellent. So that gives me, let's see, I'm going to just erase this to clear some space at the top of the board. Okay. So the magnitude then of del r del u crossed with del r del v would be the square root of, this would become 4u squared plus 4v squared plus 1. Okay. And if I want, I can factor out that 4 from those first two terms. So that's 4 times u squared plus v squared plus 1. Okay, so then to get the surface area, I would be integrating over D, which is this disk in the UV plane, the square root of 4u squared plus 4v squared plus 1 dA. But generally speaking, when I'm integrating over a disk, I prefer to switch things to polar coordinates. So I can do that. Now notice, there are no r's and thetas here. I am switching from UV, which are rectangular coordinates, to r theta, which are polar coordinates. So when I do that, I'm going to get that this dA will become r dr d theta. I'm going to get that extra scaling factor because I am switching from one set of coordinates to another. Okay. Then this just becomes the integral from r goes from 0 to root 5, theta goes from 0 to 2 pi, and this was nicer when I had it written this way, 4u squared plus v squared, that just becomes r squared. So I get root 4 r squared plus 1. U and v are just names. They're playing the roles that x and y usually play. Okay, so now I can do a lovely w sub. Let's let w equal 4r squared plus 1. So then dw is just 8r dr. Looks like I've already got my r. I'm going to need a factor of 8. So I'll counterbalance with a 1/8 on the outside. And then I can say we're getting 1/8, the integral from 0 to 2 pi. My r values will change from 4 times 0 squared plus 1 becomes a w value of 1. Let's see, root 5 squared is going to be 5 times 4 is 20 plus 1 is 21. And then we're integrating root u, or u to the 1/2, du d theta. All of that becomes my du. All right, so that's 1/8 integral 0 to 2 pi. That's going to become 2/3 u to the 3/2 evaluated between 21 and 1 d theta. So that's going to be 1/8 integral 0 to 2 pi times 2/3. I'm going to factor out that 2/3. Okay. And then we're just going to get 21 to the 3/2 minus 1 to any power is just 1, and that's d theta. Okay. Now, that's just a constant, so I'm going to get this constant on the outside, and I can cancel a 2 and a 4, so I get 1/12. This constant, 21 to the 3/2 minus 1, times the length of that interval, which is going to be 2 pi. Okay. So that's the surface area that I got here. Setting things up initially in terms of parameters u and v, then switching to polar, which involved introducing that scaling factor of r. Now what I'm going to do is just write down up here that this was 1/12, 21 to the 3/2 minus 1, times 2 pi. Oh, you know what? I can cancel something. I can cancel a 2 with that. So let's make that 1/6, and then just times pi. So that's the answer that we should get. What I'm going to do is come back in the next video and do the same problem again, but use the parameterization in terms of r and theta. So we won't be in a situation where we're switching from u's and v's to r's and thetas. We're going to have r's and thetas from the beginning. We should get the same answer, but there won't be this additional factor of r because I'm not going to be switching from one system to the other. Essentially, that r will be part of calculating what this is in terms of r and theta from the very beginning. Because now, instead of having just my first coordinate being u and my second coordinate being v, it's going to be r cosine theta, r sine theta. So those formulas for expressing x and y in terms of r and theta are part of the parameterization when I use r and theta as my parameters.